later. Okay. So good evening. Welcome everybody to this webinar about machine learning. We will be waiting for more people to join us, but for everyone who came on time, I want to say thank you. Thank you for joining us, and we're excited about you spending this evening with us. Our presentation is going to be about an hour, and if you have any questions, please save them till the end. We'll be answering them, and if you have any questions, just write them down or put them in the chat, and then we will be answering them in the end. Also, for everyone who joined us tonight, we prepared a special offer for those who will stay till the end. And we are going to spend about an hour together tonight. And I'm very excited about learning with you more about machine learning industry, how to become machine learning engineer. And I will shortly share with you about our company and just give you a few facts. So the Black Screen AI project was started in 2016 in California. And originally, we started it for those people who didn't even speak English, who just moved to US and they were looking for new opportunities on the market. And so we launched the company and we had so much success with those who weren't even native speakers that we decided to make it available for those who speak English as well. And so since 2016, we had over 3,500 graduates who successfully completed one of our courses. And also they found the job. And generally, we do have over 25,000 students from all over the world joining us. And we do have different courses, different IT programs. And today's presentation is dedicated to machine learning engineer profession. And I'll have our instructor Kevin sharing more information about this profession and career. But before we jump in, I just wanted to share with you a few more facts about our company. And let me show you. Those are just few of our graduates. And originally, the company was called FAST. And but for English speakers, we called it Black Screen AI. And we already have few programs which are successfully completed. And the course about machine learning engineering, we're starting the new group, and you will have a chance to join us today. For everyone who is joining us or who just joined, let us know where you're joining from. And I want to say welcome. And we are going to be learning about how to become machine learning engineer tonight. And I'm very excited to welcome you. So those are just few pictures of our students. And as you see, we started in a as a meetup group, and we were doing classes in different locations. But because of the internet now, people from all over the world can join us, and we made these programs available online to save you, from travels, and it just makes it so much easier. So those are just few of my favorite stories from our graduates. And why do I share them? Because I want to encourage you that no matter what kind of background you have, if you decided to learn it and you have a desire, you're ready to put effort in it, sky's the limit, and anybody could become machine learning engineer. Just think about Demir, who moved to US, and he tried pretty much everything. And then he finished one of our programs, became full stack developer, and now he's successfully working in the field. Kate, she worked previously in tourism sphere, and so she didn't have any experience, but now she works in IT industry and have that flexibility which you have to have in the times we're living in. Michael used to be a truck driver. Now he has a dream job and flexibility of working from home and generating pretty serious income. And so pretty much our students are working in any company, you name it. And IT world keeps developing, and so it's never been a better time to become machine learning engineer because this industry is blooming. And I wanted to share a few facts about this industry. So the global learning market size was valued at 8.43 billion in 2021. I checked statistics for 2022, it was over $19 billion. And it is expected to grow by 38.8% in a year. And by 2030, the market is projected to reach over 209 billion. So you could see that it's never been a better time to get into the industry, have the skill set, because it's only going to be developing. And with the instability we're living in, just think about COVID, what happened in 2020 and where we are right now. You have to create a stream of income where you have the stability, you have flexibility, and you generating the income, which allows you to have the lifestyle which you deserve. So I really like the statistics, and I want to encourage you to stay with us till the end so you could learn more and take an advantage of this industry and the market and become a professional as a machine learning engineer. So another statistics I wanted to share is that 76% of companies, they prioritize AI and machine learning over other IT initiatives in 2023. That's why the projections that it's going to grow over 200 billion by 2030, which is incredible. 47% of digital and mature organizations already have a defined AI or machine learning strategy in place. And it's very important to take an advantage of learning the skill set right now. 64% of businesses, they report using machine learning in some form, which with the highest adoption rates in the tech, finance, and healthcare sectors. As I showed you in the previous slides, you name the industry, the company, our students have potential to be working there because pretty much every company right now, they have to have the professionals who have the knowledge of machine learning in their company. And today's presentation, we're going to be talking about neural networks and machine learning. We'll have an introduction, and I have Kevin with me today, who will be your instructor if you join our program. And Kevin, I want to introduce you and I want to say thank you for sharing your experience. Kevin is an expert in the field and he's got a lot of experience, but Kevin, I'll just let you introduce yourself and tell them more. So if you have any questions, please write them down in the chat or keep them till the end. Kevin will be able to answer them. And also, we did prepare a special offer for everyone who stays with us till the end. For everyone who just joined, welcome. If you're watching this recording, I want to say welcome to you and thank you for taking time to invest in yourself, in your knowledge, and getting the skill set, which will help you to go to the next level. So welcome, everyone. Kevin, I'll let you continue.
Hi, everybody. My name is Kevin. I want to make one administrative point so that there's no confusion. I am not currently assigned as an instructor for the machine learning course. That might change in the future, but I don't want you to sign up and think that I will be there and then I'm not. So a little bit of a miscommunication there. As was pointed out, I have many years of experience in the machine learning and AI space. Recently, I've been working as a machine learning engineer, but I've also done some teaching work and some work as a data scientist. So machine learning fundamentally is about statistics and patterns. The goal is to take a very large corpora of data, so corpora just means a large set of data, and examine them to identify a pattern of interest. And we're always interested in statistical patterns. So the end result of a machine learning system is always going to be probabilistic. There's always going to be some chance or some randomness involved. Machine learning harnesses randomness to do its work. And you've probably, as was mentioned at the beginning, that this is a lecture about machine learnings and neural networks. Well, to put it simply, neural networks are just one kind of machine learning algorithm. They're one way to solve a problem. They're one of the most well known at the moment and among the most successful, but there are a lot of other tools that can also be used. And one of the things that you learn as an ML engineer or as a data scientist is when to use what tools. And neural networks are often the right choice, but it's worth pointing out that there are others. So in this first start of the lecture, as someone who's a machine learning engineer, it's my job to take, so some data scientists, they go through some data and they develop a model. They develop some solution to a problem, but it works on their computer and only their computer. A machine learning engineer's job is to take this model that has been carefully designed and turn it into something that goes from working on one computer to rolling it out to millions of people. So that the model that was developed that predicts whatever is being predicted can be applied to everybody and can be run every day successfully without any issues. So that is what a machine learning engineer does. They go from between when the model was created to where it actually reaches consumers. And I see 6 general steps in building such a system. First step is the goal. You need to know what problem you want to answer, and you need to be able to make it very clear and mathematically precise. Second step, you need to have a source of data relevant to that goal that you can pull from. Third step, pre-processing. Data is always imperfect. There are always problems with data. So data needs to be cleaned, it needs to be organized, and it needs to be turned into a format that can be used to you. Fourth step, now that you have some data that's been cleaned to a level where you can actually use it, you need to decide what algorithm you're going to use. Neural networks, maybe a support vector machine, or linear regression, or any number of the dozens of machine learning algorithms that are applied. Next step is to take the model that you've built and determine how well it's doing by building metrics that measure the performance and quality of the model. And the final step is that when you actually have this model that does a good job, is to roll it out to consumers and to have the built model produce predictions. So if there are any questions at any point, please put them in the chat. Also, that's my excuse to take a drink of water. So in these next few slides, we're going to go through each one of these 6 steps and get a gentle introduction. We won't be going into the math of machine learning at the moment, but just to be clear, any machine learning engineer needs to have a good, solid mathematical foundation, which any course in machine learning will provide for you. To give you an example, before this work, I worked at Capital One, and a big problem at any bank is fraud detection. So the idea is that I have a list of transactions. Transaction here means name of account from which the data came, name of account to which the data is going, how much was sent, and when. So I just have perhaps billions or millions of such transactions. And I also have some knowledge of previous fraud. So some of these are identified as fraudulent and some are not. And it's my goal that given a new transaction that I haven't seen before, predict whether that transaction is likely to be fraudulent or not, based on the information about the previous transaction and whatever patterns we can draw out of it. So this is going to be our example that we're going to use today when we go through each one of these 6 steps. How will we apply these steps to this problem? First step, goal. It is not enough to be able to say, I want to know if there's fraud, or I want to know if my ad campaign is working. You need to be able to say something that is mathematically precise and measurable. So, for instance, in the example of, is my ad campaign working? A better question would be, how frequently do users actually click on the ad? Or what percentage of users actually click on the ad? And it is always important to be able to link that goal to the data. If you have a goal, but it doesn't match your data, it doesn't help. So if I'm trying to identify fraud and you give me a bunch of information about hospital records, that isn't a problem that I'm going to be able to solve. So being able to clearly define the goal and then connect it to a data set is the most important, is the fundamental question that needs to be asked. So in our fraud detection example, as I said, we have a list of transactions and we want to know for a transaction that has recently occurred, is it likely to be fraud? And at what likelihood is it to be fraud? And by fraud here, I mean the transaction wasn't authorized by the account's owner. There are perhaps other kinds of more complex fraud, but we'll just focus on the straightforward example at the moment of was this transaction actually authorized by the account's owner? Data. Data is at the heart of every ML system. It is one of the biggest expenses, one of the biggest limitations, and one of the biggest assets that any company can have. Recently, there have been a number of large language models which are processing data, and companies that have access to very large quantities of data have an advantage. But also, companies that can cleverly use the data they have, that can pull information about data that they have access to that other companies do not, have a serious advantage. So being able to identify your data set and being able to have consistent access to it is one of the key things that any company will need. And as a machine learning engineer, one of my jobs is to ensure that this constant stream of data that's coming in from wherever the source is something that can be relied on to produce new systems. So what do we mean when we say the data is good? Well, in machine learning, we use the term signal and noise. This is unsurprisingly taken from the signal processing field. Signal is meaningful information that is in some way connected to the goal. So to give you a separate example, let me backtrack. A noise is random variations within the data that does not impact the signal. Noise is your problem. Noise is something that doesn't have anything to do with the problem at hand, that just prevents you from being able to solve it. So in our fraud detection example, it's likely that the amount of the transaction is a useful signal. If the amount of a transaction is markedly larger than anything else that that account user has ever produced, that's highly suspicious and worth mentioning. If, to consider a noise example, if I have access to the address that the account user is using, counting how many letters are in that address is data, it's information. It's also likely completely useless in determining whether this problem is solvable. So that would count as noise. There's also noise in the sense that there can be variation in these account transactions that are not the result of fraud and that need to be discounted. So as I said, being able to identify this source of data and link it to signal of this problem you're trying to solve is one of the most important problems. Just to clear some terms, the entire data as a whole is either called a corpora or a data set. An entry or row is one example. In our transaction set, the data set is every single transaction that's occurred so far, and an entry is a single transaction from a single user. Labels are markers that indicate the correct answer, as it were. So in this example, while we have the transaction, separately from that, we may also have a label, in which case that means that some reliable source, a professional at the bank or the account users themselves, have indicated that this transaction is fraud, or they've assured us that this transaction is certainly not fraudulent. And depending on your data set, we can have some, all, or even none of the entries are labeled. And by also getting labels can be one of the most expensive processes. So large companies have entire groups that are just dedicated to designing these labels. If you've ever done one of those CAPTCHAs where you're asked to determine what a picture is, you get a bunch of pictures and you say, please choose which of these is a stoplight. Congratulations, you are labeling data. That's what you're doing. You're identifying which pictures are stoplights and adding that label to them. Data is messy. Here's my example. I was working on a project that involved patents. Specifically, I was working on German patents. And one of the processes I had to do takes longer the longer a sentence is. And one of my patents was taking hours. It was just sitting there. And I was trying to figure out why. And it turns out that German patents have sentences that are literally hundreds of words long, which turned out to be a problem because my algorithm was causing problems with that. So I needed to find a way to fix that problem. I needed to reorganize and remanage these sentences so I could deal with the fact that these sentences were much longer than I would have expected. There are always surprises in data. And so in our transaction example, we can think of a lot of problems that occur with the data. First of all, there's not mentioned here, but worth noting is the security and privacy aspects. We need to be aware when building the model of how likely we are to have problems with security or privacy. Is the way we're storing the data secure enough? And are we sure that this model will not leak private information to anyone outside of the bank? On a more mundane level, we have the fact that transactions occur in several different currencies. So you can have one account making transactions in yen and euros and US dollars, and we need to be able to clean our data in such a way that we can compare them in a meaningful way, so that we can know that, hey, this transaction that's in dollars is much larger than the transaction in yen. And that is an indication that it might be fraudulent. The timestamps of these different transactions may be from different time zones, and we want to know if a transaction occurs on an unusual time, then that's suspicious. If the user has never done a transaction at 10 p.m. at night and suddenly does, then that's something we need to be aware of, and we need to first deal with the fact that there are other time zones and adjust for that. I'm sure you can think of a bunch of other things that need to be organized and cleaned. Preprocessing is always a surprisingly long step. That's one thing that I often try to warn new people in the machine learning business, is that preprocessing has the tendency to take longer than you think it will. And that's why they hire machine learning engineers. Now we have our data. We've determined the problem we want to solve, and we've identified that our data has a signal that can be used to solve that problem. We've cleaned our data so that it has as many of the problems removed as we can think of. And now we need to actually make a prediction. That's what the model does. Model is an algorithm that's designed to pull the signal out of the data. And there are 4 basic categories of model, or if you want to think about it, 4 different kinds of machine learning problems. Supervised problems. Every entry in the data set has a label in a supervised problem. A transaction is either fraudulent or not fraudulent, and that's it. Unsupervised data. There is no label at all. All of the generative AI that you may have seen, all of the large language models, the interactive chatbots, that is all running on unlabeled data. Nobody has gone through and told you anything about the data. You're just learning patterns about the nature of language, and that's how the chatbot works. Semi-supervised models, kind of what you would expect. It's halfway between supervised and unsupervised. Because how expensive it can be to generate labels, sometimes we only want to generate some of the labels and not all. So we'll select a small portion of the data to have labeled. We will perhaps pay someone to generate those labels for us. And then we have some part of our data that's labeled. So how can we leverage that small portion of labels to the entire data set? And reinforcement learning is a different kind of problem. Reinforcement learning can almost be thought of as trying to play a game. So I have some model that's going to perform an action on the world. Then the world will tell the model whether it's doing well. The model will adjust accordingly and perform a new action. Driving a car is an example of reinforcement learning. I look out at the world, meaning my sensors of video and audio and GPS. I make a decision on what to do, drive, turn, stop, and then I get input from the world. I see how my cameras have adjusted to the new information, how the world around me has changed, and then I make a decision as to whether or not the action that I just made was a good one or not, and I move to make a better action in the future, one that is safer and gets me to the destination faster. The same kind of problem can also fall into several different categories. For instance, our fraud detection algorithm could actually be either supervised or semi-supervised. We may not know if every single transaction is fraudulent. We may have many transactions where there has been no information about whether it's fraudulent or not because it's so mundane that we haven't actually had a guarantee that it is or is not fraudulent. But we have important transactions that are marked as fraudulent. On the other hand, we may actually have information about every single transaction and know whether or not it's fraudulent. In that case, it's supervised. In the former case, it's semi-supervised. Being able to look at your data, decide what kind of problem it is, and therefore what kind of algorithm needs to be applied is fundamental to data science and machine learning. Models are algorithms. They're tools to solve a problem. But unlike most computer science algorithms, like your quicksort or insertion sort or whatever the other sorts you want to think of, these are models that are designed to update their results based on input data. And we say that a model is trained when it has examined a data set and used and been built to make a prediction or complete a task. One of the important things that you need to do with the data is you need to break it into parts. We often break it into 2 or 3 parts. In the example of 2 parts, we're going to break it into a training set and a test set. One of the fundamental ideas is that when we're trying to determine whether the model is successful, which we'll talk about in a minute, we cannot look at information that the model has previously seen. If I ask someone whether they're good at determining if something is fraudulent or not, and I give them a bunch of examples of fraudulent transactions, and then I show them the same transactions and ask them if they're fraudulent, I can't tell if they're actually good at it or if they just memorize the transactions. So we always give the model data it has not seen before. So when you take your full data set, you usually break it into parts. One split would be 80% training, 20% test. The training set is used as the model examines it, looks at it, and learns a prediction. And then the test set is handed to the model afterwards, and it makes a prediction about each element of the test set. And the result is used to generate a number of metrics. There are a lot of metrics. Accuracy. What percentage of my results are correct? Mean squared error is something you may have seen if you've taken a statistics class. It's used to measure the difference between a number and the predicted number. We can think about area under the curve or the ROC curve, prediction, or precision and recall. There's a number of different metrics that the course will go into in full detail. Knowing which metric is correct, which metric is the right one to use is good. And as a machine learning engineer, I also have a number of metrics that are not related to the quality of the model, but rather to the efficiency of the model. How long does it take for this model to run? How much memory does it use? How long does it take to train versus how long does it take to generate a prediction for the user? Can it be run on the user's phone or does it need to be run on a server? These are all questions that need to be answered about an individual model before it can be rolled out to people. So here's an example of the steps that you would go through if you wanted to solve a supervised learning problem. First, we take the training set and we hand it to the model, which is then used to train the model. The model updates its predictions based on the training set. In this case, the model has access to the labels. It can see the answers and uses them to learn. We then look at the test set. We take away the answers. We take away the cheat sheet, and we just show the model the unlabeled data, and we ask it to make a prediction. Then we take back the cheat sheet and we compare the model's prediction with the actual results. We use those to predict a metric. So for example, simple accuracy, what percentage of the model's predictions were correct? Then the model examiner looks at these metrics, looks at the quality of the model, and makes a decision about how to improve that quality. Change what model is being used, update the data set, add more data, or perhaps fine-tune the model when making a few adjustments to some inputs. And that process is repeated over and over again as the model improves until the model has an accuracy or quality that is sufficient for the task at hand. Now that we have a trained model, this is the step probably where the machine learning engineer, the 2 steps where the machine learning engineer needs to do the most work are at the beginning in the pre-processing and then at predictions. If you have a model that has been trained to produce predictions, you now need to actually use it on the data. So in the fraud detection example, you need to build a system whereby every single transaction that's passed through the bank first passes through your model to determine whether it's fraudulent. And if that model says it's fraudulent, or if that model says it's fraudulent above a certain percentage, then you need to make some decision as to what to do. So for instance, if the model says it's fraudulent above 90%, you need to contact accounts owners and determine if the model was correct. Now we're going to switch topics a little bit here. This was the introduction to machine learning as a topic. Our next slides are going to be about how neural networks work specifically. This would be a good time for any questions about the machine learning section of the presentation. So there's also an excuse for more water. Cheers. So I'll give you a minute. If there are any questions on any of this stuff. This is a high-level overview. Any class will go into much more technical detail about how each one of these steps is done. Okay. If not, then we'll move on to the next section. Neural networks. A neural network is a kind of machine learning model. So all of those steps that we looked at, the pre-training, the data, the processing, neural networks are one way to make predictions. They are intended to mimic the structure of the human brain. They're not a direct analogy to the human brain. And in fact, one of the advantages, or one of the great improvements in neural networks came when they start to think of them as a separate thing and examine them separate from how the actual human brain works. But just like in the human brain, your brain has a number of neurons, very small cells that connect to each other in a complex network where each individual neuron is very simple and does one very simple task. But by combining them together in the correct structure, you can have a system that is designed to do much more complex and much more powerful tasks. Generally, when we design a neural network for convenience and for organization, we often organize it into layers. So we'll have a layer of neurons, which then connects to another layer, which then connects to another layer, so forth. This is everything. This is the entirety of a neural network. This is a single neuron as it's described. So here we have X1, X2, and X3. Each of these represent inputs to the neuron, either the results of a previous neuron or fundamental data itself. That information is then passed to the neuron. However, it's weighted. So what the neural network is learning are these weights. So we want to learn that, for instance, for this problem, X1 is far more important than X3, and therefore weight 1 should be higher than weight 3. And the process of training the neural networks is the process of adjusting these weights. As you go, the weights are either increased if they're relevant to the problem or decreased if they're not. The result is then summed, to which a bias term is added. A bias is just some constant term that's applied to this neuron that helps balance things. At the bottom here, you can see the basic formula. Each neuron has an activation function, a function that is applied to its results before it is handed off to the next neuron. One of the fundamental ideas from a mathematical perspective is that the activation function of a neuron must be non-linear. By linear, I mean it must not be a straight line. It must be any other function. And if you're mathematically inclined, something that you could do at home is that you can prove to yourself if every neuron in a neural network had a linear activation function, you could, in fact, collapse the entire network down to a single layer. Mathematically, you could just turn the whole thing into one layer as a result of the fact that each one is linear. The disadvantage is that because they are nonlinear functions, we cannot use any of the tools from linear algebra to simplify the calculations, which is why training a neural network takes so much time. The activation function is applied to the sum of the weights times the inputs plus the bias. And the result of that is the neuron's output. Here are some example activation functions. On the left, we have the rectified linear unit, or otherwise known as ReLU. The advantage of ReLU is that it cuts off at 0. So one of the things we want to be able to do is limit how many weights there are in a network. If we can get more of the weights to be exactly 0, or more of the outputs to be exactly 0, it is much easier to store and much more less processing, which has made the rectified linear unit very popular recently. The sigmoid and tanh functions are less cut off, and that more organic nature makes them very useful for other kinds of problems. We won't go into when these functions are used. That is beyond what we can get into today, but this is one of the fundamental things that needs to be understood for neural networks, is when each of these functions should be used and how. Using a neural network consists of two tasks, one called forward propagation and the other one called backwards propagation. Forward propagation is the process by which the neural network actually makes a prediction. Data comes in, it's applied to the weights, which is handed to the neurons, which apply their activation function, which hand on to the next layer, and so on until eventually the network spits out a result at the final layer. This is the fundamental way that neural networks produce predictions of any kind. Backwards propagation, or sometimes referred to as backprop, is the secret sauce of a neural network. It's the process by which a neural network is trained. Specifically, we start with the result and work back to the beginning. So we perform a pass of forward propagation on an individual piece of data, and that generates some prediction. The neural network says that this particular transaction is likely to be fraud. We then look at the real label. Let's say for the moment that, in fact, this is a fraudulent transaction. In that case, the network was correct. And all of the weights in the network that contributed to that correct example should be increased. And all of the weights that did not contribute to that correct example, or that were leaning towards indicating that it was not fraudulent, should be decreased. And this is how the network is trained. You start with the last layer and you work your way backwards, updating the weights as you go, depending on whether or not the result was correct. You use an algorithm called gradient descent, which you may have heard of in your your calculus classes, which is something would be covered in a full class. There are several different kinds of neural networks. The image on the left here indicates what is referred to as a feed-forward neural network. It is one of the simplest designs for a neural network. You have some inputs coming in on the left. They're being handed to neurons, which then are applied to the weights indicated by the different strengths of the lines, which then lead into another layer, and then so on. A convolutional neural network is one that's commonly used in image processing. If you built this kind of feed-forward neural network, where each one of these inputs on the left was a pixel, and you were looking at a standard image, you would have billions of neurons. You would have far too many neurons. You'd also have a network that was very fixed. Instead, we use what's called a convolutional neural network. We build a tiny neural network, and then we walk it across the image, one part at a time, and apply the same network to each part of the image. That has two advantages. One, the network is as a result much smaller. We're only considering a grid of maybe 100 pixels at a time. And two, we're trying to identify where something is in an image. If we're doing that, determine if this is a spot or traffic light thing. The advantage of that is that if we see two images of traffic lights, one where the traffic light is in the upper left and the other one where it's in the lower right, that same convolutional neural network will identify both of them because it's being applied to different parts of the image. A recurrent neural network is a network that is appropriate for data that is time sensitive or in some sort of linear fashion. Specifically, it's a network where the layers roll back on themselves. So in this case, we might have this second layer feeding data back to the input. And then when the network is run again, we now have results from the previous run as well as our access. Recurrent neural networks were very popular in processing language up until very recently, when the large language models came into effect, but they're also incredibly useful for time-sensitive data. A fraud detection algorithm a recurrent neural network might be a reasonable result for a fraud detection algorithm, because one of the fundamental things we want to know is this transaction very different from the previous transactions? So we can use a network that has loops or has structures to it in that way. Okay. I want to share with you all a link as soon as I can pull it up. This is, I'm going to put this in the chat. This is from Google. It's, what would it be on? It's a website in which you can play with a toy neural network and train it. It's an excellent tool to help you understand how a network works. So you can redesign the network, adjust the weights, and try to see if you can solve the problems at hand. Okay, questions?
Kevin, that was great. That was a lot of information, and I want to say thank you to everyone who is still with us. I have an interesting question from Alexandra. Yes. I don't know if you can see it in the chat. You want to answer it?
I know that there are frameworks that can help you with ML. Can you please give an example of what kind of Python programming tasks would also need to be used? I'm trying to expand the complexity of programming. So in terms of frameworks, there's a number. Two frameworks used for neural networks are PyTorch and TensorFlow. PyTorch is more Meta and TensorFlow is more Google, but they're both used by several different companies. To process the data, we generally use packages called NumPy and SciPy. NumPy deals with numbers and SciPy deals with mathematical calculations. There's also a package called Pandas. Pandas is designed to just process data. To understand the complexity of programming, generally when you're dealing with a machine learning engineer, what you're doing is you're taking each of these individual packages and you're trying to connect them together. So you take Pandas, which then grabs your data, perform some calculations using NumPy, adjust the data in the appropriate way, and then hand that data off to PyTorch to actually run the neural network. So the task is often one of understanding these packages and the math behind them sufficiently well that you can then connect them together. It's actually somewhat surprising how short the code of machine learning is. Machine learning code is notoriously quite short. And compared to other areas, it's often far less lines of code that are doing far more work per line. Let me know if that answers the question.
Yeah, Alexandra, let us know. That was great. Yeah, she said thank you. Anyone else, if you got technical questions about machine learning industry, Kevin and answer it right now. I have a question, Kevin. What is your favorite part about machine learning? Like, in your opinion, since you've been in the industry over 10 years, you know, tell us who can become machine learning engineer. Actually, like I had my next slide about it. And do you think the person has to have like statistics mindset, like very technical, or anyone can learn it? What's your opinion?
I think anyone can learn it, but I won't hide this fact. You will learn statistics. Like, there's no getting around that. You will learn probability and statistics. But if you go from first principles, then anyone can learn this material, but you are going to need to learn some math along the way. It's interesting math. It's math that can be applied to a lot of really fascinating problems. It's the math of probability and statistics and randomness and what events are likely and what events are not likely. So it's math that is also applicable in the real world. It's also a very concentrated and focused mathematical area. You do not need to learn all of mathematics. You need to learn a few specific formulas and equations and ideas, and you need to understand them well enough to apply them, but you don't need to know everything.
That's great. So you can learn it. You just need to put effort into learning, right?
I mean, it's like anything else, you know, there are lots of areas where you need to understand probability and math that are not necessarily math or probability focused. I've been told that Apparently, there are some people who are in this field who just took the LSAT for no other reason than they were curious, since there's a lot of probability questions on that test. So just like that, you need to be able to think in those ways. I see another question. Comparing quality assurance automation, software engineering, and machine learning, how easy will it be to understand the topic and find a job nowadays? Okay, so quality assurance automation, if it's not already, it probably will start to use machine learning models to generate these quality assurance. So quality assurance is the process of determining whether a particular piece of code works correctly. It's the thing that's designed to prevent that crowdsource problem that we had a few days ago. That's what quality assurance does. It's designed to identify problems like that. And if it's going to be automated, it wouldn't be surprising if there was some math involved. Quality assurance automation is all about thinking of edge cases, thinking of potential problems before they happen. It's a very problem-oriented mindset. You need to be able to think of what could go wrong and how do I prevent it. Software engineering, machine learning engineer is a kind of software engineering. QA automation is also a kind of software engineering. So I would consider that like the overarching subject into which quality assurance automation, machine learning engineer, and a number of other sub areas fall. I don't know for you which one will be easiest. They're very different kinds of problems. I know for myself, I find that I naturally fall to machine learning much more easily than quality assurance. The idea of trying to think of every possible problem that could go wrong is less ingrained into my mind. But for someone else, they can do that without thinking. So they're both really excellent areas, and they share a lot of similarities, but they are different ways of thinking about things. And it's more about what you as a student excel at. So in that case, if you're not sure, I would suggest a very gentle introduction to both and see which one is sparking your interest more.
Wow, that's a great advice, Kevin. And also, like what I wanted to say that it's very rewarding profession as well. And as I shared some facts with you in the beginning. The industry is booming, and the starting salary is $110,000, and there is always room to grow. And the market is only going to be developing. And if you would be comparing with like software engineering, that it's usually 3 to 4 months course. And with machine learning engineer, we design a 6 month course. So it would be enough time for you to kind of like go through it and understand and learn it. So it's not a short-term program, it's at least 6 months. And then we'll also offer internship. And I will kind of like, this is just the statistics. If you check Indeed, average salary of machine learning engineer in United States. I don't know what it is in Canada, but approximately probably maybe a little bit less in Canada, but in US, that's average salaries. And so we take you step by step through the learning process, where by the time you complete the course, you don't just have a knowledge, but you also complete, the internship. Will help you with your resume building, and it's not like 1 or 2 month course, because it does involve statistics, creating the models, but it is very challenging, but in the same time interesting process where you learn, you stretch your knowledge, and you get the reward for that as well. So you will learn a lot of different techniques, models, applications. And Kevin kind of like shared with you introduction lesson today. There is more to learn, but I'm very grateful, Kevin, for you giving kind of like a system where you shared with the steps of going through it. I really like that, and I think that helped to a lot of our future students to understand what it is about, and it's like the first step. And you're ready for the next one. Let me explain you what we prepared for all of you who stayed with us. If you got more questions, put it in the chat, or we're still able to take them and answer. I also wanted to share with you what exactly included in the 6 month program. So as I mentioned already, internship, it is going to be a real project. So you would have real time experience. So by the time you get to job, you would already know how to apply that skill set, which you learned during the course. We help you with your resume. We even do the mock interviews and prepare you. Also, I know some people they're on Eastern time, some people in Pacific, so we do provide you recordings. And if you feel like you need to retake course later on, you know, it's available as well free of charge. Also, uh, timeline, as I mentioned, is 6 months. So you start your practice in the middle, internship, career coaching. So our students, they're able to get the job because they don't just get the certificate of completion, but we also give them practical knowledge. And that allows our students, once they get the job, to keep the job because they don't just have theoretical knowledge, but there will be a lot of interaction, a lot of practical assignments, and so that all helps us to allow our students to be successful in this field. And so classes are going to be 3 times a week. It's 1 hour per class, and in Pacific time, it's Tuesday, Thursday, and Saturday. Tuesday, Thursday, 7 p.m. So if you are in Eastern, it's going to be 10 p.m. But if you feel like it's a little bit late, you can always rewatch it next day when it's more convenient for you. On Saturdays, it's going to be at 10 a.m. Pacific, so that would put you at 1 p.m. Eastern time. And as I mentioned, if sometimes you have some events planned on Saturday, you can always rewatch the recording. And what makes our program and our school different from anybody else there is that we keep our groups small. So in this case, it's almost like one-on-one classes with the instructor. So we try to create a group no more than 15 or 20 people. And in this case, it's not like the lecture with 100 people where if you didn't understand something, you kind of feel lost. And I don't know if anyone been in a situation like that where you paid a lot of money and then you didn't get the value out of the course. And that happens all the time. So we decided that we are creating this small group where we know each student, we help each student, uh, we track their success and we help them to get from the A to B, where by the time you completed the program, you feel confident, not just how to get the job, but how to keep this job and how to develop yourself so you could go to the different levels. So if you start with $110,000 a year, there's always room to grow and you can go to over 250 with the time and effort and practice, of course. So this is just the parts of the training program which you will be learning. But if you would like, we can send you the full curriculum and you can pretty much learn everything you would like to. But we do include all the important programs, and I listed a few of the parts of the program which you will be learning on the slides, which is important to know in order for you to get the job in the industry. And for those who stayed with us today, we did prepare the special offer. And usually this program costs way over 6,000. Our offer is 5,999 for those who join us today. If you need to make some payment arrangements, you can use this QR code, put $49 deposit, and then make some payment arrangements and join us today. If you're ready to join right now, feel free to scan the next QR code, or if you have any questions or you need individual payment plan, feel free to use this QR code so you can join us. Or if you have any questions, just feel free to fill that form. I see that someone is asking, is the internship a mandatory part of this course or are students looking for it on their own? So it is a part of the course. So unless you're already in an industry and you don't have time for that, and or you have friends who, for example, work in a similar company where they offer you internship, but we make it a part of the program because it's important for us not just give you the theory, but we want you to apply what you learn during the course. So you would feel confident in your first day job, you would feel like you know what to do, and you don't feel that stress, of not knowing what to do. So that's why we make it a part. And which companies? We partnered with different companies, so you would be able. I mean, it depends, which company has different projects. We can just add you to. So, but it is a part of the program. So, if you're ready to join us, you're more than welcome to do it right now. If you have questions, you want consultation, please use this QR code. But I want to encourage you to invest in yourself, because I understand the importance of investing in yourself, because we live in this times where things are unpredictable, and you have to have a lifestyle you deserve, and you have to have a skill set which will allow you to have that lifestyle. And I want to encourage you, invest in yourself, and create the future where you have flexibility and you're generating a great stream of income where you can do things you would like to do. And I always say that preparation, uh, success is when preparation meets opportunity. And as we mentioned earlier, there are a lot of opportunities on the market right now, but you have to be prepared. You have to have a skill set. And that's why we created the system, which will allow you to get the skill set, get the job, and be on the next level. Because if you do nothing right now, 6 months down the road, you'll be in the same boat, regretting that you didn't take the action. And the successful people, they take action when they see opportunity, and this is a great opportunity on the market. What is the difference between English and Russian courses? I noticed the difference in duration. The main difference is language. Uh, Obviously, different instructors. The duration, the English speakers program is 6 months, and we see that it's enough. And internship will be included in 6 months. So we're not gonna let you do internship the first month you get started. So you gotta get at least foundation. So once you got the foundation, then we will be able to add the internship probably in a few months down the road. And then if you feel like you need more internship, we offer that option as well. So scan this QR code. I'm going to go through general questions. And if you have any more questions, please put in the chat. We'll be answering them. If you have some questions about the program, Kevin is still here, so he'll be able to answer it as well. The course will be starting on August 6th. As I mentioned, for English speakers, it's 6 months, 3 times a week, 1 hour per class. And the schedule, like if you miss the classes, as I mentioned, we do provide the recordings. But because the group is small, we're able to kind of like if you misunderstood something, the instructor usually gives you extra time where he can answer your questions. If you didn't understand something, you can reach out. And because the group is small, you're not going to be lost in the knowledge. So what's included? Mentorship sessions, mock interviews, interview coaching, resume building, internship, pretty much everything you need to be successful in this field. We designed the system which will help you not just to get the knowledge and another certificate, but we take you step by step, and we help you to get the job and be in this field successful. Real experience resumes, I kind of answered this question. And so let me return to the previous slide. Make sure you scan this QR code if you have any questions, or if you're ready to join us. You can use this QR code, the previous one for the deposit. And as I mentioned, this is a 6-month program. So, and it's important to invest in yourself so you would get that dream job. And if there's something what's stopping you, just don't get stuck, move forward, take action. As I mentioned, the difference between successful people and not successful is that successful people, they're taking action, and when they see opportunity, they don't miss it. And if you compare finishing this program, you can spend years in the university. You can spend like 4 to 6 years, get the diploma, and then not everyone is using their education. Here, and actually, that would cost you a lot of money. I would say at least $100,000 a year of investment. Here, you invest $6,000, and in 6 months, you get the career, which will take you to the starting level of job of over $100,000. So that's no brainer. So I encourage each of you to take action right now. Join us for this program. Do not miss this opportunity. If you have any questions, as I mentioned, please scan this QR code and leave your information so we can get in touch with you and help you to get started. I also want to say thank you to Kevin again for being with us. And we're very excited about each of you who will take this action and create a future you deserve. So thank you for being with us today. We're looking forward to talking to you soon and helping you to get started. I hope everyone will have a wonderful evening, and we'll see you at the top. You're welcome. You're welcome, everyone, and have a wonderful day.